Okay, so we're going to have the last lecture of the day. So we have Nicolas Durrande, who is a senior machine learning scientist at Prowler.io.
Yeah.
He was previously at École des Mines Saint-Étienne in France.
And previously at the University of Sheffield as a postdoc in Niels group. So hi everyone. I'm here to talk about kernel design. So you've seen most of it during the lab session you just did. So hopefully you'll have a lot of questions during the talk. So feel free to interrupt me anytime you want, right? So here's the short introduction. You've already seen a lot this morning about Gaussian process and Gaussian process models. So I just have 2 slides to set up the notations I've been using. I'm using the letter uppercase Z for the Gaussian process. And we've seen this morning that the distribution of a Gaussian process is characterized by 2 things, its mean function and its covariance function. So there's no condition on the mean function, but the covariance function is the body of the model, and I'm going to talk a lot about this covariance function during the talk. What can we do with covariance functions and what we can't do with covariance functions. So here's the equations you've seen this morning for what is the conditional distribution of a Gaussian process given some data. And we've seen that it's a product between matrices or vector and matrices that involve the kernel function a lot and the vector of observation for the mean function, and that involve just the kernel function for the covariance, the predicted covariance. And that's one way, a typical way to represent the model, just with the mean function and 95% confidence intervals. All right. So what is a kernel? So we've seen that the definition of a kernel is K of XX is the covariance between the GP evaluated at the 2 inputs of the kernel. So since K of XX corresponds to this covariance of Z of X with itself, then this is just the variance of Z of X. So the kernel value if you repeat twice the same input, has to be positive, greater than or equal to 0, because this is interpreted as a variance, and we know that a variance is positive. There's another property of the covariance that directly tells us something about the kernel, is that the covariance is something that is symmetric. Covariance of Z at X and Z at Y is equal to the covariance of Z at Y and Z at X. So K of XY must be equal to K of YX. If someone tells you, oh, look at this kernel function, or look at this covariance function, and the function it gives you is not symmetric, or is not positive if you plug twice the same input, then that cannot be a valid covariance function. We can obtain a result that is a bit more precise than what we just did. And the idea behind that is to introduce a new random variable that will be a linear combination of the GP evaluated at some arbitrary location. So this is just a univariate random variable, a classic one. And if we compute the variance of this guy, so this is the covariance of the linear combination with itself, and we can use the linearity of the covariance operator, and we end up with this expression, and we recognize in here this is just the kernel function, so we end up with this quantity. So this variance is equal to this quantity. And we know that the variance is positive, so this quantity over here, whatever the kernel you consider, has to be positive. And this is the definition of what we called a positive semi-definite function, all right? So according to just these 2 lines, any covariance must satisfy this quantity. And the opposites also happen to be true. Any function that is symmetric and positive semi-definite, you can use that as a kernel function for a Gaussian process. All right, so there's an equivalence between these 2 concepts, like being a covariance of a process and being symmetric and positive semi-definite. That's all you need to use a kernel into a GP model. All right. So if you come back to the expression we have for the conditional mean and conditional variance, if you have a function that satisfies this quantity, you can plug the kernel into it, and you will have a probabilistic interpretation of your model. All right. Any question on that? Okay. So from the definition of a function proving that a function is positive definite directly from the definition is kind of tricky, because if you look at the definition, it has to satisfy this, whatever the number of elements you're summing over, whatever the value of A, and whatever the location over here. So most of the time, a direct proof of positive definiteness is not possible. But there are, in the literature, a vast amount of functions that have already been proven to be positive semi-definite. So you can choose any of these and build GP model based on any of these covariance function. So the most common one would be the Mattern covariance function, the squared exponential, but you also have like some very classic, like the Brownian covariance function. You have basically as many as you want. In this list, I could add the spline covariance function. So some people do spline model, but spline model are nothing but GP model, just it's for a specific covariance function. Or we've seen this morning that with linear covariances, you can recover a linear regression model, for example. So that's a vast number of covariances that will lead you to a vast number of models. And so you can see two parameters in these expressions. The first one is, like, we usually call it sigma square. It is in front, and we usually call this parameter the variance parameter, because if you look at least for the first 4 GPs that are over there, if you look at k at xx, so this will be the variance of the GP at x, then like, we'll have exponential minus 0, because if y is equal to x, this is equal to 0. So k of xx will just be equal to sigma square. So the variance will be equal to sigma square. And that's true for this kernel, this guy, and this guy. So for many kernel, this sigma square can just be interpreted as the variance of the GP. That's why we call it the variance. And this guy is the length scale, which is just a rescaling of the inputs. So let's look at some of the kernels that we can find, how they look. Normally, you've seen that during the lab. Here, I haven't been using GPy. I've been using GPFlow, which is similar, but the kernel that I implemented are not exactly the same. And so quite a lot of kernels look just like hat functions. So what does it mean to have a covariance that look like a hat functions? It means that this is the kernel evaluated in. So I fix one of the variable to be equal to 0, and I plot it just as a function of the remaining variable. And if you look at this is the value 0. So we have a hat function that is centered around 0. So it means the value of the GP at, let's say, 0.01 is going to be very highly correlated to the value of the GP at 0, because this covariance is high. The kernel represents the covariance between the value of the GP. And if you go further away from 0, then your covariance decays, and you will have less and less covariance the further away you move from the point. So the information you have from one observation in X will tell you, will have less and less value the further away you go from X. It's something that is quite natural to have in many applications. So this is why these like hat-shaped covariances are kind of common. But they don't all have this form. For example, for the periodic kernel, so for polynomial or linear kernels, they don't have necessarily this hat function, but it's quite common to have a kernel that has this shape. And now if we look at the GPs that are behind these functions, this is the kind of samples we obtain. So it's very important to have in mind that when you do a model with one of these kernel, what you're actually assuming the prior you put inside your model to do your inference is actually one of these type of functions. So of course, if you change kernel, you will end up with very, very different posterior. And this is because when you change kernel, you change the prior assumption you make about the function you are looking at. So for some of them, you have samples that are going to be continuous but not differentiable anywhere. So these, for example, could be interesting if you want to model the value of, I don't know, like a stock or an option through time. It's not something that is very regular. If you look at like stock options, it's something that changes quite a lot with time. So this is the kind of assumption that would make sense to model just the markets. And if you model physics with some of the types of physics that will include more continuity, more smoothness in the function to look at. Then you have all different degrees of smoothness. So for example, for Maten 3/2, your samples will be differentiable once but not twice. For Maten 5/2, they will be differentiable twice but not 3 times. And for a squared exponential kernel, then they will be infinitely smooth. So you will have all the derivative that will exist. So it's basically, when you're building a model, you should think, what assumptions can I make about the function I want to approximate, the function where the data comes from? And then you should pick a kernel that satisfies the assumptions you want to make. So choosing a kernel is choosing the information you want to put into your model. That's the idea you should have in mind. So, so yes. So for some of these guys, we can prove directly from the definition that they are positive semi-definites. A very easy one, for example, is the kernel for the white noise. I can do that on the board very quickly. So if I take the double sum over I and j of alpha I, alpha j, xj, if you remember for the white noise kernel, k of xi xj will just be 1 if xi is equal to ej and 0 otherwise. So this double sum over all these terms, all the non-diagonal elements, let's say here, are going to be 0. So this double sum is just equal to a sum over I of ai, or I can write that ai square. So this quantity is going to be greater than or equal to 0. All right, so for some simple kernel, we can do the proof directly. But for the other one, it will be not possible to come up with a proof that is simple like that. So there's one trick that is very common to prove the positive definiteness of stationary kernels. So stationary kernels are kernels that just depend on the difference between the two inputs. Is this result that is called the Buchner theorem, that says that any function, so if a kernel is stationary, it depends on just the difference of the two variables, and I'm going to write that k tilde, right, to just say the function of one variable and this variable being the difference of the two inputs of the covariance. So Buchner theorem tells us that any function that is positive semi-definite can be written like this. So it is the Fourier transform of a measure that has a finite mass and that is positive. So now, instead of showing something is positive definite, we just need to show that this quantity here is positive, which is much simpler, just saying this measure does not take negative value. So let's look at an example. If we take this measure, it is something that is positive, like it's equal to 0 everywhere except on this interval. And we know that if we take the Fourier transform of this kind of function, we end up with a sine t over t function. So according to Buchner theorem, this is a valid covariance function. It's something we can use and plug into GP models. All right? So if you want, you can use that into your models. We can also use Buchner theorem to show that many usual covariance functions are positive definites. So for example, if you take the Fourier transform of a Gaussian function, you still end up with a Gaussian function. And we've seen that the RBF kernel, or the squared exponential kernel, is itself a Gaussian function, right? So that proves that the square exponential kernel is positive definite, just because it's the Fourier transform of something that is positive. And for the Mattern kernel, they are the Fourier transform of this kind of function, this kind of spectrum. And again, this function is positive, so all the Mattern kernel are going to be positive definites. All right, so that's the proof to show that we can use Mattern kernels. And there's some work from Andrew Wilson that uses this theorem to build new covariance function. So he parameterized the kernel by a sum of Gaussian in the Fourier space, in the spectrum. And since everything here is positive, we know that by taking the Fourier transform, we'll end up with something that is a valid covariance function. And the Gaussian over here, so this is just a sum of Gaussian, so it's parameterized by the location and the width and the amplitude of each of the Gaussians we are summing over here. And you may notice that this guy is symmetric, so we symmetrize the function here on the power spectrum because we want the Fourier transform to be real in order to end up with a GP that has value over R and not over the complex numbers. But this is just one way to parameterize the covariance by what's happening in the spectral space. And we end up with a covariance function that is stationary, but that can have this kind of behavior. And there was a question this morning about, is that a problem that a covariance takes negative value? And no, it's not a problem at all for a covariance function to take negative value. It still can be positive definite. It's just saying that the value over here will be negatively correlated to the value of the GP here in 0. So this is typically what we observe if your signal kind of has wave. So if you are very high at one point, if you know you're behaving as wave, you'll probably be very low if you move from half a period, all right? So this is what we observe on the samples of the GP. So they are not periodic, but they do have this oscillatory behavior of functions. But the period or the phase function may change over time. May change over time because if you look at the value of the GP over here is not correlated at all compared to what is happening over there. So you may have a phase shift that is happening between this point and this point. Do you have any question on that? No? So now how to choose the appropriate kernel. So this is the same data on the two graphs, just I fitted a model with two different kernel. So now, do you think one of these models is better than the other? There's a good and a bad answer to this question. So people could be tempted to say that this model on the left is better because it has lower, it's more certain about what is happening. So we like to reduce uncertainty, so this model is better. But actually, we can't tell which model is better because it depends. Like if we add an extra observation over here, if the extra observation is there, then our model is terrible. It's very highly overconfident about what is happening. We want the confidence interval not just to be small. We want them to be realistic about the uncertainty we have on the prediction of the function at that point. So there's no way when we just look at these two models to say one is better than the other. And if these two models are so different, it's because they are based on a different kernel, so they are based on different priors, on different assumptions on the model. And for the one on the left, we are making this kind of assumption for the function to approximate. On the one on the right, we make this assumption. So of course, if your true function is like that, then the best model is this one. But on the other way around, if the true function is very wiggly like a stock market, then this will be a much better model than the one we have on the left. So when you want to choose a kernel, what you should think about is what assumptions can I put into my model. You can't create a model without making assumptions. If I just give you a set of points and I ask you, okay, can you predict me what is going on at that point where I don't have any observation, and I don't want to make any assumption about the function I want to approximate, then there's no way you can make a prediction. If the function you want to approximate is just completely discontinuous and going crazy all the time, then there's no way you can predict anything about what is going on. On the other hand, the more assumptions you can put into your model, so the more regularity assumptions you can make, the more precise your model will be and the more informative it will be. All right, so modeling is having data, making some assumptions about the underlying function, and then combining these two things according to Bayes' rule. But we need to make assumptions, and choosing the kernel is not something which say, I don't really like the idea of trying all the different kernels I can and then just pick the best model. I prefer to think about what assumptions do I want to put into my model, and this is what I like about GP model, is that we can interpret the model we are making, we can look at what assumptions we are actually making. So a good practice, if someone gives you some data, or if you generate the data yourself, is to ask, what can I assume on this function? Do I assume it to be stationary? That's the first thing. So being stationary means it's a difference of the input, but another way to look at stationarity is to say, is my covariance between 2 points likely to change if I move my 2 points together in the space? For example, if the variance going to be constant, or is the variance going to be greater and greater? Can you have a feeling about that? If it's reasonable to make a stationarity assumption, then put this stationarity assumption in your model by choosing a stationary kernel. You can also ask the practitioner, like if he expects something about the regularity of the function you have to approximate, and then to choose a kernel accordingly to these regularity assumptions you can make on the function. And the more assumption you can make, the more certain your model will be, the more informative it will be, but you don't want to make assumptions that are not realistic. All right, and a good thing to think about is also trends. So trends can be incorporated in the mean function of the model, but they can also be incorporated in the kernel of the model. We'll see that later on. And also some particular patterns like periodicity, cycles, or additivity. Just try to gather all the things you can on your data. If the practitioner tells you, okay, this is the solution of this differential equation, then you should look, can I get a kernel where the sample path actually satisfy this differential equation? Like Rich was saying earlier on, like if you have a curl-free function, then you should look for a kernel that will give you curl-free sample path, for example. And then your model will be extremely precise compared to one model that ignores this curl-free property and that just generates samples. So gather as much information as you can, and then try to pick a kernel that satisfies this assumption. And we've seen that kernel usually depend on some parameters, and this is something that is quite difficult to ask to a practitioner. So what do you expect the variance to be, or what do you expect the length scale to be? They usually won't have any answer to that. So sometimes they will give you a range, but they don't necessarily understand what a length scale is. So the common thing is just to estimate this guy by doing maximum likelihood estimation. Another way is to do leave one out estimation, so try to minimize the prediction error. And or you can also go back full Bayesian and do some MCMC if you're able to have some prior for those parameters.
How do you define the prediction error when you have confidence intervals?
I say it a bit on this slide. So the first thing you can do is you take a test set, and then you look at the prediction of your model at your test set. So you should look at, is the mean value right? Like, is your mean value not too far from the predicted thing? And if that's right, it tells you that your mean is actually accurate, so you can use your mean, or basically you'll have an idea of what error you typically make by using your mean. You also want to make sure that your confidence intervals make sense. So typically what you do is you look at the error you make, and you divide this error by the standard deviation predicted by the model. And that should be a variable that is Gaussian with 0 mean and variance equal to 1. And you can do that for all the points of your test case. And then you have a bunch of random variables that are supposed to be N01. So you can plot an histogram, and you plot on top of that the density of a N01 random variable, and you would like these two things to match. They won't match exactly, but you want them to be a reasonable fit for your histogram. So that's a way to validate your confidence intervals. Another way is to look directly the mean negative log probability. So that's kind of the log likelihood on your test set. But basically, you want to check if the mean is all right. You want to check if the confidence intervals are all right. And ideally, you also want to test if your predicted covariances are right. So if you take 2 points in your test set, then your model is going to return a covariance for these two guys. And you can look at, in average, is the random variable you observe on your test set, like the error you observe, is it in the distribution that is predicted by your model? And if that happens to be the case, then you're great, you're good to go with the model you have. Maybe it's not informative enough for what you want to do, but at least you know it's realistic, its predictions make sense according to what you can do. And if you're unhappy with the result of your model, so the typical thing to do is to look at other covariances, like do you have something wrong in the elicitation of your covariance? And other things you can do is to try some remapping, either in the input space or in the output space, to kind of try to make the data look more Gaussian. So it's always worth trying a couple of transform on the input or output just to see what comes out.
Is it standard to generate a p-value for testing the?
It's not that common to use p-values. So we do that a lot just in linear regression, but then you have a null hypothesis on the coefficients, and here you don't really see the coefficients of the model, right? You don't do p-value on the error, you do p-value on the estimated value of the coefficients, and here those are non-parametric models, so no, it's not common to do p-values. Is there any other question? Yes?
You mentioned it like confidence interval makes sense and predicted covariance are right.
So this is to see if your uncertainty, your pointwise uncertainty is right. And this is to see if your model also predicts covariances between two test points. All right, so you can also check, you should also check if this predicted covariance is right. You can have models where the confidence intervals are right, but where the predicted covariances between 2 points are wrong. It's a bit similar, but it's also a bit different. Yes?
What does it mean for the confidence intervals to make sense? Like how would you judge whether they're right?
So it's, are they realistic? So you have, so if your test points are, I don't know, let's say, located something like that, and if you look at the standardized, so you have the error here in this quantity. If you divide this error by the standard deviation over here, you can make an histogram of all your errors, and you're going to end up with something like that. And then you should compare that to the distribution you're actually expecting them to be, and hopefully you will end up with something like that. And this is what I call like the confidence intervals make sense. The uncertainty that is predicted by the model is actually related to the actual uncertainty I observe in my test set. So this is what I say, they make sense. On the other hand, if your test point gives you value that, I don't know, are here, then your model is highly overconfident, and when you're going to do this histogram over here, you're going to end up with, I don't know, an histogram that is something like that, and you're comparing it with this distribution, and this is saying the error predicted by the model is not related to the error you observe in reality. So your confidence intervals are not realistic.
This is going back to the covariance, predicted covariance. Are you comparing it to the training covariance matrix, or?
So no, I'm using here, like to standardize the residual, I'm using the posterior covariance, the conditional covariance. Yes?
Can you give intuition why that should be zero mean variance?
So we've seen this morning that if you look at samples from the prior of your GP, if you look at one point what is happening, these guys should be normal. K of xx. All right, so this is valid for the prior. So for the prior, if I take the value of my GP here, I subtract the mean, and I divide by the standard deviation, the square root of this guy, then I would expect my variable to be distributed n01. All right? Now, when we are doing the same thing here for the posterior, we also say that the posterior is also a Gaussian process. And what I'm saying here is that if I look at what's happening over here, I expect these to be n0 where this is the conditional mean and this is the conditional covariance that I had on the second slide. So if I, in these points, my model is telling me that my data should be Gaussian distributed like that. And in practice, if I observe a quantity over here, if I subtract the mean and divide by the square root of this guy, then that should again be N01. All right? Any other question? OK, so that's again something you've seen during the lab. So if you have any question about the lab, just ask. That would be the right time. So you should have seen that you can sum kernel together, and you will still end up with something that is positive semi-definite. Or you can multiply kernels together, and you're, again, going to have something that is positive semi-definite. And something that was not in the lab, I guess, is you can compose kernels with functions. I'm going to give examples of this kind of transform, and we'll see what's happening.
What assumptions are you making on the functions there? So that would be also Gaussian process?
This guy?
Yeah.
No, I'm not making any assumption on this. It's an arbitrary function.
Arbitrary, okay.
Yeah. We'll see later why. So let's look at the sum of two kernel. So if this is positive definite and this is positive definite, then this guy will also be positive definite. And this is something that can be proved directly from the definition. If you remember, if I write the double sum over AI, AJ, something like that, I can just split this in two double sum, AI, AJ, K1 of Xi, AJ, plus the double sum over J, K2 of Xi, Xj. And if K1 is positive definite, this term is going to be greater than or equal to 0, and same for this guy. So just directly from the definition, we can prove that a sum of two covariances is still going to be a covariance. And here's a quick example. This is maten 1/2 covariance, or the exponential covariance, plus a linear covariance. I end up with this function that is kind of linear, but with a small tilt due to this guy. And yeah, I can use that in my model. It's something that makes sense. Now, what assumptions am I making when I'm doing this transformation? I'm actually assuming my GP to be the sum of two underlying GPs, one with the kernel K1 and the other one with the kernel K2. So we have it just here. If Z has this covariance, then we can see Z as the sum of these two guys, where these two guys are independent, and they both are distributed with kernel K1 and K2. Because if you look at the covariance of this guy, the covariance of two independent things is going to be the sum of the two covariances, and you're going to recover K1 and K2. So making a model with the kernel we had on the right is basically saying, I expect my function to have kind of a linear trend plus some variations that are continuous but not differentiable anywhere. So that can make sense, again, to model the stock market or something like that if you want. But when you make the sum of kernel, it's very easy to interpret as what's the underlying assumptions you want to make. Now let's see on an example how that can be useful. So that's a very common data set in machine learning. It's the recording of the CO2 concentration in the atmosphere in an observatory in Hawaii. So I plot it as a function over here, but you should actually see this data set as just a lot of observation points. There's one observation, I think, every month. And we have data for 50 years or something like that. So now let's try to predict, using all these data points, what's going to happen in the future. So if I take an RBF covariance, or a square exponential kernel, I basically have this two choices I can make for the length scale of the GP. I can either say, OK, so I have some high frequency variations in here, And you remember that high frequency variation means taking small value for the length scale. All right? So if you take small value for the length scale to reflect these high frequency variations, this is how the model is going to look like, which is a bit crappy, right? The confidence interval kind of makes sense, but the mean value is very off. No one believes that in 2020 the CO2 concentration will be back to 0. I think that would be pretty bad. Okay, so this model is not good. But by the way, do you understand why this model comes back to 0? Is it something you understand, or is it something you find surprising?
Back to prior?
Yeah, exactly. It's going back to the prior. So with a very short length scale, you're basically saying there's no correlation between what is going on in 2010 and in 2012 or something like that, because the covariance decays very, very quickly. So if there's no link between what is happening in 2010 and 2012, then your model, if you want to predict what's happening in 2012 and your last data is from 2010, then your model is basically saying, okay, you're giving me some data, but this data is kind of very far away because my prediction right now is not correlated at all with what was happening before, because that was too long ago. I had time to change in many, many different ways. So the data you're giving me doesn't have any information for me. So I'm just going to predict the prior because the data has no information in it. So this is the model going back to the prior, and here I was using a GP with a mean equal to 0, so the mean reverts to 0. And this is the standard deviation that was estimated. So a very bad model. On the other hand, we can say, okay, I can see a large trend in this data. So I'm going to take a squared exponential kernel with a long length scale to reflect for this trend, to account for these low frequency variations in the signal. And this is the kind of thing you obtain with a mean that would kind of follow the trend. So this is actually what you want. The mean is kind of right here. But the confidence intervals are wrong, because if you predict what's going on in the near future, the model is telling you that I'm very sure about what is happening over here. And in practice, it's not true that the true concentration is going to be in this range. We expect it to keep oscillating with this 1 year period, all right?
Did you add the linear kernel as well?
No, there's no linear kernel in here. Everything is given by the square exponential kernel. So if you go and predict very, very far away on the right, you're going to come back to this, to a mean value that is 0.
There's no examples. I would expect it to go.
It's extrapolating for some points, and in some time, I don't know, maybe in 2100 or things like that, it will just revert to the mean value that is 0. It will do that in a very long time. So another thing we can do is to sum two kernel with a square exponential. So as before, one with a very short length scale and one with a very long length scale. And this is the kind of model we end up with, which is much, much better. So what is the assumptions we are making by summing these two kernels? We're saying, okay, I expect this signal to be made of two GPs, one with a long length scale that will go for the trend. So probably a long length scale and a large variance to explain this trend that has large variations, and another one with smaller length scale but also a much smaller variance to explain that I have some variability around this trend. So by taking these covariance, we're just saying, okay, I expect two kind of frequency to be present in my signal, low frequency and high frequency, and probably with a very small variance for the high frequency, just to account for these variations around the mean. All right, but now the model is much better, the mean makes sense, and the confidence intervals also make sense. But we can do even better we know there's some periodicity in this data set because there's a 1 year periodicity in the carbon dioxide concentration due to just the seasons. So we can include a periodic covariance in it to account for this periodicity. We can also say, I don't want the model to revert to 0 in a very long time. I do believe that at least for some time, I'm going to have a quadratic trend in this signal, and then the model would just kind of revert to the quadratic trend where it's very far away from the data. And now this is the kind of model we end up with, which I believe is a very good model, a very good prediction about what's happening over here. Yes?
To some extent, could some of that be in the mean as opposed to being in the kernel? Zero here.
So yeah, you could put the quadratic effect in the mean if you want. The periodic effects, maybe you can do, but it's not as straightforward as this one. Is straightforward to put into the mean because it's just one basis function. For this guy, it's still you can choose a periodic kernel that is non-parametric, so that would correspond to an infinite number of basis functions. So you can't put it into the mean.
The first time it would be equivalent to put it in the mean, or if there is a nuance in the modeling?
So for the first one, it would be exactly equivalent if you choose for this parameter a very large value. If you set this value to infinity, then you will see no difference between putting these components into the kernel or having a quadratic term into the mean. So for large value of this parameter, you're not going to see a difference between having it as a mean or having it in the covariance. Any other question? Yeah.
So in this model, you would be very interested in the confidence intervals that in the extrapolated area.
Yes.
Would you, to establish like whether you think those are right or reasonable, would you use the same method that you described before with pulling out a test set and checking it on the known?
Yeah, I would pretend I only have observation up to these points, and then look at the prediction of my model, and then see if they are or not in what I predict over here. And I can do that like a lot of time. I can do a swipe of all the data just by predicting what's going forward, and then I can check if do I believe my predictions over there or not. That's the thing to do next. Yeah. Any other question?
So
Yes. Sorry.
Oh yeah. Could you learn the period of the periodic kernel as well?
Yes, you can. It's a free parameter. You can.
Like a lot of local maxima to your observation model.
So in this one, I fix the period to 1 year because I know it's a natural phenomenon and it's not going to change. Like I can believe that 1 year will still be 365 days long in 20 years. So here I don't want to learn it, but you'll see at the end of the talk I have an example where I learn the periods of the periodic kernel. It's just a parameter of the kernel. Yes?
In regression, it seems very easy to paint oneself into a corner when you have correlated variables. But here it seems that you are suggesting that we can basically combine different kernels in a lot of many degrees of freedom in terms of combining kernels in different ways without this actually risking leading to a worse model. Is that true? And if so, what's the intuition?
So yeah, in a way you have to be a bit careful. So what we typically do for the parameter of this kernel is we do maximum likelihood estimation. So if I add kernel, I basically give more degrees of freedom to my model. So my maximum likelihood is always going to be better because I can just put one of these variants to 0, switch off one component. So I can always retrieve a model just based on one kernel. But here I have more degrees of freedom, so my maximum likelihood is always going to be better. So it's not such a good idea to compare models like that just based on the maximum likelihood, because the more kernel you had, you're going to say, oh, it's improved all the time. So one thing people usually do is to look at the BIC criterion, the base information criteria, to make sure they're not adding too much parameter to their model. So yeah, maybe that's the correct thing to do to make sure you're not adding too much degree of freedom. Like the degree of freedom you're adding to your model are actually worth it. So when we were doing this sum of covariances, we were adding covariances that were taking inputs in the same space, right? Everything. On the other hand, you can sum two covariance functions that are defined on different input space. So here I make a covariance function over a two-dimensional space. So if I sample from this GP I'm going to obtain just functions of two variables. One sample will be a function of two variables. I construct this function where x is a two-dimensional vector and y is a two-dimensional vector by summing these two functions. All right, so it's again summing kernels, but that are defined for different input spaces. So this is the way I represent it. As before, I can interpret a GP based on this kernel as a sum of two GP. One is defined over the first dimension of the input space, and the other one being defined on the second dimension of the input space. So if I sample from this kernel, I will see functions that look like a sample in x1 plus a sample in x2. So if someone tells you, oh, here's the data, and I believe that there's no interaction between these two variables, like I expect my output to be a function of x1 plus a function of x2, you should jump on this information right away, and you should choose these kind of covariances to add this knowledge into your model. All right? So, of course, what I just said, that these kind of kernel are very interesting if you want to approximate additive functions. They are also interesting if you want to make model in very high input spaces, because additive models are quite robust to increasing the dimension of the input space. So yeah, there's a whole theory about the GAM for generalized additive models, and you can do generalized additive model with Gaussian processes just by taking sum of kernels, and that can be very helpful in high dimension.
Does it make any sense to sum those kernels but with a weighting, and then apply a regularization to the weights to reduce the possibilities of overfitting?
So when I sum these two kernels, I usually include, like inside this expression, there's already a weight parameter that is included, that is the variance. Right. So you can have like a small variance for one of the GP and a larger variance for the other GP. So yeah, there's naturally a weighting that comes in it.
But can you penalize those? You know, can you treat them like weights in a regression and then put a penalty term on those to emphasize because when you add all of these kernels together, or however you compose them, whatever operations you use, I mean, you could tend to overfit, right? Because you're allowing much more structure to be captured by this combination of kernels with all of their free parameters.
Yeah, but what Rich was showing this morning is that there's already this regularization term that is embedded into the model. We already have this. If you want to show that GP is equivalent, when you show that GP is equivalent to regression, you show that GP is equivalent to Rich regression. So you already have this penalizing term inside the GP model. So you don't want to add it again. It's already there in all the models we're looking at. So now, if we look at the mean function of our model, so it's the same expression as before. So this matrix here is actually the sum of K1 plus K2, and this term over here is the sum of K1 plus K2. So I can expand with respect to the first term. I end up with this term here and this term on the right. And these two guys, they can still be interpreted as a conditional expectation of the model. So M1 is the conditional expectation of Z1, given that I observe Z1 plus Z2 is equal to my vector of observations. So when you want to predict what is happening just with respect to the first variable, you see the contribution of the second variable as noise on top of your model. You don't observe directly what you want to approximate, you observe what you want to approximate plus something you want to get rid of in your prediction, if you're just interested in how does that behave with respect to M1.
So if upstairs is also your observations matrix as well, is that what you're saying?
Say it again?
F at the top as well is your matrix of observations.
Yeah, those are the vector of observation, yeah. So this is what we observe if we look at the prediction variance. So this is an additive model in 2 dimensions. And around the observation point, I'm going to have a variance that is equal to 0. And when I move away from the observation point, my predicted variance is going to grow up to recovering the variance of the prior. So there's one thing. So this is for a classic kernel, like a product kernel. And this is what we observe for additive a model with additive kernel. And we can see that there's no point. There are points where we don't have any observation, but still the variance gets reduced in those points. All right? Can you tell why?
It extrapolates along each axis, you get those two.
Yeah, like these 3 points will explain this one, exactly. If you know that your function is additive, knowing the value here, here, and there is going to tell you what the value of the function here is over here. So basically the value here is going to be this value plus the increment you have from here to there because of the additivity assumption. So the model naturally knows that even if it doesn't have observation here, since the model must be additive, then it's quite certain about what's the actual value of the function over here. All right, so we have this that comes naturally just by choosing the right prior that tells us the additivity assumption. I'm going to pass on this guy. OK, so we can make sum of kernels. You've also seen during the lab that we can make product of kernels. That's still a valid covariance function. You can make product of kernels defined over different spaces. That's still a valid covariance function you can play with. And you can compose a kernel with a function, which is what I was talking earlier on. So whatever the function f is over here, so it can be an arbitrary function, this is going to be still positive semi-definite. You can either do the proof directly from the definition, or you can just notice that this is the covariance of the GP defined by z of x equal to z of f1 of x. So it's just a remapping of the input space, but that's still a GP. Like remapping the input space does not change the fact that we still have a GP. Right? So here's an example where we combine a Matern kernel with this kind of rescaling. And this is the kernel function, which is not stationary anymore. And this is the kind of sample path we obtain. So very high frequency variations in the beginning, and then it's becoming smoother and smoother with time. OK, that's the kind of thing you can do with this rescaling. And of course, all the transformation I've been talking about can be combined together. And for example, this quantity here is going to be a valid covariance kernel. Can you tell me why? So this can be seen as a product of f of x, f of y times k. So k is a kernel, and this guy is also going to be positive definite because this is the composition of a linear kernel with the function f. The linear kernel is x times y, and here I don't have x times y, I have f of x times f of y, but this is just a combination of linear with the function. So this is positive definite, this is positive definite, and I'm taking the product of these two guys. So I can plug that into my models, this will work. And if I take the same transformation as before, this is the kernel I obtain, and this is the kind of sample path I end up with. It's just something with kind of a non-stationary variance, with very high variance around 0, a variance that tends toward infinity in 0, and just a variance that becomes smaller and smaller when we move away from 0. So we can put this information in model. If the practitioner tells you, I expect a bigger variance in 0, just make a kernel of your own that has this information into it, right? I'm going to skip this because we don't have that much time, and I'm going to talk about something I was working on kind of a long time ago, because that was when I was doing my postdoc in Sheffield, but it's relevant to the talk, so let's talk about it. Let's say we have this kind of data, and we want to extract the periodic component of the signal. So we are going to design a covariance function that will have a periodic component and something that is not periodic. So what is it not to be periodic? It's something that if you project on a basis of sines and cosines function, you end up with 0. And we can actually take, for example, a Matern covariant for this guy, and we can decompose, we can see this GP as a sum of two independent GP, where One is exactly periodic, and the other one is exactly orthogonal to periodic function. And if you derive the kernel of the periodic component, this is what you end up with, where B of x is the vector of the Fourier basis, and this is just a matrix that is a gram matrix, and this is the aperiodic component that writes as this difference. So if we have a Mattern kernel over here, we can end up with this decomposition. And if we can end up with this decomposition, as we did before, we can split the model into two submodels, and this is what we end up with a model that stands for the periodic part and a model that stands for the aperiodic part. And each of these two models can be interpreted as conditional expectations, so we also have uncertainty that go with our two models. So this is what we end up with. We started from data, we fit a model with a Mattern kernel, and then we can decompose this model as the sum of two submodels, one being periodic and the other one being not periodic. All right, we can do a bit better. So we started from a kernel, Mattern kernel, that has a variance and a length scale parameter. But now that we write this kernel as a sum of two kernels, we can also tune these parameters independently in the two submodels. All right, so we now have 4 parameters to characterize our kernel, and we can add an extra parameter, W, that stands for what is the period I expect for the periodic component. And we can estimate all these 5 parameters by doing maximum likelihood. And this is the kind of model we end up with. And the model recovers exactly the function I've used for this test case, which is a periodic function, a sine, plus a linear function. And the model is quite sure about what is happening over here. So just by having some knowledge that I expect this to be something periodic, but plus something that is not periodic, then we can build a much better model because we gave the model the right degrees of freedom just by specifying the right covariance function for it. And we use that to do some gene expression analysis. So this is for Arabidopsis, and we wanted to identify the genes responsible for the circadian rhythm. And so there are 22,000 genes, and we just have 13 time points, which is not much. And then we can compare with the literature to see the data that we assume to be the genes that we assume to behave periodically compared to the genes the literature assumes to be periodic. And this is the kind of genes where we disagree with the current literature. And so those are genes that were identified as periodic in the literature and that we don't identify as periodic, or they're not in the set of the most periodic genes. Why don't we think they are that periodic? Because there's either a lot of noise around it or some trend or some function on top of it that make them not that periodic at all. And on the other hand, this is the genes we have identified as periodic and that were not recorded as periodic previously. And we can see that we have some sharp spikes that kind of ring every 24 hours. So we were very happy to see these genes appearing even if they were not in the initial genes considered as periodic. So once again, we try to give the right degrees of freedom to the model, the right assumptions about it, and this is the kind of model you can end up with. All right? And as a conclusion, so when you change the kernel, you change a lot the result you're having, so you have to be careful about choosing the kernel. I've seen too many people saying, oh, I've tried Gaussian process model, or I've tried Kriging and it doesn't work for my model. But most of the time, it's just they plug the first covariance function that was by default, and they ended up with a model that was making no sense. And they just threw all GP models. But for me, most of the time, it's just a misspecified covariance. So it's worth spending some time on the choice of this covariance. And yeah, the idea is to encode with the kernel the prior belief you have about the function you approximate. And in many cases, you can tailor your kernel to your problem at hand, and you really should do that to end up with very informative models. And so we've seen that Bochner theorem can be helpful to build kernels or to prove that kernels are positive definites. Making new from old is a very good way to easily create new covariance functions. And the part I've skipped is about linear operators. So Rich was saying that earlier on, that if you have a mapping, a linear mapping that goes from any function to a function that has the property you want. For example, you can find a linear mapping that will take any function and return to you a symmetric function. Then you can use that to build a kernel that will generate linear sample path. Right? Symmetric sample path. So if you have linear operator that map a function to what you want, then you can build the right kernel. The kind of thing that are difficult to do with GPs is when the mapping you're interested in is non-linear. For example, it's impossible to have a GP where that is monotonic, right? You can't find a linear mapping that will go from any function to a monotonic function. So GPs are not a very good tool for approximating functions that are increasing or functions that are positive or just functions inside one given range, because you don't have linear mapping that goes to this space. You can't define appropriate covariance functions to encode this knowledge. Right, do you have any question? Yes?
Yeah, so my question is about fitting this type of parameters. We're talking about a lot about choosing the kernel and combining them and then having all kinds of parameters.
Yes.
Fit those parameters. So would you also do, how would you structure this in terms of your training and your validation of your test sets? Would you add there much like validation sets? So would you do it like that? Like fit another train set, choose all those hyperparameters on the validation set, or?
So ideally, you will have 3 sets: one for training, another one for testing, and another one for validating in the end. Otherwise, you may overfit your testing set if those two are not separate. A common thing to do is, we like this model, they are very data efficient. So usually, people with very little data, like we had for 13 points, is because getting data is expensive. So you don't have as many points as you have. So it's quite common to use leave one out for the testing before you do your validation. Any other question? Yes?
Is there any mechanism to really leave out the outliers? Because like GP tries to fit every point.
Yeah. So when we do GP regression like that, and when we have a solution in closed form, it's because we assume that the noise on the model is actually a Gaussian noise. And then we can derive everything analytically, and we have our models that we are happy with. But if we have some outlier inside the data, probably having a Gaussian noise, so having a Gaussian likelihood is not the right thing to do. You want to have other types of likelihood with heavier tails that will be able to explain outliers. So if you do the same thing, and if you apply the Bayes rule with a likelihood that is not Gaussian, then, for example, a student T likelihood, which will have a heavier tail, then you do not have closed form solutions anymore. But this is a kind of model that will be interesting if you want to model data with outliers. And you will have a talk tomorrow morning by James Hensman on this, how to fit GP model with non-Gaussian likelihoods. And this is the model you want to go if you have outliers in your data.
But then you go to variational inference as well.
Yes, and then you go to variational inference or to MCMC. Yeah. There's no closed form anymore. You need to approximate your posterior. Yes?
Can you mention about time series? A couple of words, how do you apply to time series in the Gaussian processes?
Okay, so we've seen one example, the CO2 was applied to a time series. What people usually do with time series is Kalman filter type of models, because they are cheaper to compute than the model we've just seen, because you don't have to invert these big covariance metrics. But it turns out that a Kalman filter is also a Gaussian process model, just it's a bit more clever in the way it's computing the inverse of the matrices, and the inverse can actually be computed analytically in closed form. So if you have very long time series, I would kind of discourage using directly the equation we've seen, but you will end up doing the exact same model just from another point of view. Any other question? Good, great, thanks.
Okay, thank you.
before, if you're going to the Blueberry today, there is a group that is going at 6 from here. Otherwise, you can get there by yourself. See you tomorrow.